Let me begin with a word of prayer. I'm sorry I'm starting super late and I've wasted your time with nonsense, possibly, but anyway. Heavenly Father, we thank you for this day again. I thank you for the students and just ask that you'd guide our steps today, Lord. In your name I pray, Lord Jesus. Amen. All right, so just a quick rehash of things you know from Physics 232, right? There's something called mutual induction. There's something called induction, right? And we can talk about both of those things. Now, so the basic idea is that if you've got a current in one loop, then it creates a magnetic field through another loop. And so because of how the way the formulas work here, if we focus on scenario 1, which is a current flowing through the first loop, it gives a magnetic field through the second loop. And so the magnetic field that's generated by current 1, well, if that's a steady current, we can pull I1 out, right? And so the magnetic field is directly proportional to I1. And so if I calculate the flux through the second loop, it's proportional to the current through the first loop. And because that's just a geometric thing, we can just call that, whatever that is, that number is the so-called mutual inductance. But Griffiths then goes on to show us how we can derive what's called Neumann's formula, or Newman, I don't know, whatever you like. But of course we can calculate the flux through loop 2 with the vector potential of the magnetic field from loop 1, and that gives us this. But on the flip side, we can calculate the vector potential by integrating the current density through loop 1. So we've got an integral around one loop, an integral around the other loop, put it together and it gets really loopy. You got integral around loop 2, loop 1, like this. That is a formula for the mutual inductance going with 2 and 1 as expressed in point 1 and 2 in the slide here. And that's this. But the dot product is commutative, you know? And the distance between the loops, the script R, is also symmetric with respect to the roles of 1 and 2, right? So if you look at the formula, here, we can write down M12 is the same but with loops 1 and the 2 and the 1 flipped-to-flopped, and 2 and 1. And this, I use the same symbol here because that's reasonable, because it's the distance between the 1 and the second, which is the same as the difference between the second and the 1. So it's the same separation formula. And then because we can flip the order of integration, that proves that the mutual inductance is defined without respect to which loop comes first. Right? We can either think about current flowing through loop 1 creating a flux through loop 2, or we can think about the current flowing through loop 2 creating a flux through loop 1. Either way, the proportionality constant between the flux and the current we can define to be the mutual inductance. Right? So we'll, in the 232 class, we'll then call it M. This is a beautiful example that puts this idea into practice in a powerful way. It says, you know, what's the flux through the long solenoid if there's a current I flowing through the short solenoid? So that's a very complicated problem because the solenoid is short. So to understand that, we would have to understand the fringing field, like the complicated business that happens from the magnetic field coming around here and then looping back and all that jazz. Like, it's bad, right? It's a bad calculation. But because of mutual inductance, we can flip the script and we can say, well, I can instead imagine current flowing through the long solenoid and figure out what's the flux through the short solenoid. And that will define the mutual inductance. Now that's easy because if we have a current flowing through the long solenoid, it's very, very long, we don't face the issue of the fringing field. We can just calculate the flux directly. Now, so the magnetic field from the long solenoid is just mu naught I N2, where N2 is the number density out here. Now, that magnetic flux is, that magnetic field's constant through the short loop, right? Now, what is the total flux through the short loop? Well, that depends on the number of loops in it. To find the number of loops in the short solenoid, I take the number density N1 times L. That's the actual number of turns in the short solenoid. So, oh, I'm getting ahead of the story. So, we have pi a squared, which is the area of the short solenoid, the number of loops in the short solenoid, B2, the magnetic field due to the long solenoid, and that gives us this formula right here. But that means that this, whatever that is the mutual inductance. But the thing is, it's equal to the other way around, and so phi2, the flux through the long solenoid due to the short solenoid having current I, is equal to this, which is that. This is an ingenious switcheroo because we trade a problem that's like nearly insolvable for a problem which is easy to solve. It's very sneaky. Very, very sneaky. Very cool. Now, of course, we can differentiate the flux, right? And then if we think about Faraday's law applied to each loop and, add the voltage around each loop up and up and up, then that brings us to the voltage induced around loop 2 is minus the time rate change of the flux through loop 2, right? And I say loop 2, but really we're talking about a whole collection of loops as if it's one loop. You see that in the example above. I was like, so there's some sleight of hand here in the term loop. It should be interpreted through the example. And you'll see it again in the next example. But anyway, so this is, of course, m is a constant with respect to time, right? We're not moving the loops. And so minus m di dt, that gives you the voltage induced. Of course, this is very interesting because we're talking about the voltage in loop 2 induced by a change in the current through loop 1. And these do not actually have to be physically connected, right? They just have to be somehow sharing the flux from the one to the other, Of course, this is the principle which, we use to make generators and transformers from and such, right? And then, of course, nothing's stopping us from thinking about a single loop. If we calculate the flux that's due to a current flowing through a loop, it's proportional to the current. And whatever that proportionality constant is, we define that to be the self-inductance of the loop. And so we get, E is minus d phi dt is minus L di dt. This is the so-called, I think he calls it the back EMF. In the book, he calls this the back EMF. The units for inductance are Henry, which for some reason my sister-in-law thinks is hilarious. I don't know why exactly, but she just says it's very funny. What's that? You also find it hilarious? Do you know a Henry or something, or?
No, but I think we should rather call him Millie Hanks.
Millie what?
Millie Hanks.
Millie Hanks? A Hank is 10,000 Henrys. No. It's like the Gauss versus Tesla. Anyway, so this is the toroidal coil, right? And so it's got a rectangular cross-section here, and it's looped round and round. And so if you think about the right-hand rule and you kind of imagine gripping any of these loops, you'll find that the magnetic field encircles inside the toroid, right? And you can draw an Amperian loop, sounds wrong, Amperian loop at any distance s from the center axis of this thing, and Ampere's law will quickly reveal to you that it's mu naught Ni divided by 2 pi s. That's the magnitude of the magnetic field at a distance s from here, right? Now, so to calculate then the flux through a single loop of this toroid is as follows. We, basically here's the magnitude right here, and it's area, the normal to that cross-sectional slice is in the angle which encircles the axis direction, right? Like that. And that's also the direction of the rectangle. And so I've got dA phi. Of course, phi hat is 1, and I end up with integral of dz ds over s, the s coming from the Ampere's law calculation. So I'm integrating basically z from a to b, wait a minute. I mean from 0 to h, sorry, duh. This is s is equal to a, this is s is equal to b, so we integrate from a to b, we get log b minus log a times mu naught Ni over h. Now that's just the flux through one of the big N fold loops in this toroid. So to find the total flux through the whole toroidal coil, right? Thinking of it collectively as one giant loop, which is actually like an ensemble of n loops, I multiply this by big N. That gives me the total flux through the whole toroid. And by the way, we're trying to calculate the self-inductance of a toroidal coil at the moment, if that's what we're doing. So phi total is N times phi 1, which gives us this. Well, that's the proportionality constant times I. That's merely geometric. This is the self-inductance of the toroidal coil. All right? So that's that. That's pretty neat. I'll probably use this for my Physics 232 class next time, you know? I put this in here, it's unlikely I test on this because you guys already know it, so I don't want to bore you, right? No? Yes, okay, good. Do you guys think it's boring? Yeah. It's kind of boring, but anyway, this is the LR circuit, and so we have, the current, the voltage source minus the back EMF has to be equal to I times R. I don't know, add up the voltage drops in the circuit, and you get 0, of course, and then we can solve the differential equation, and this is the solution. The interesting thing, of course, is that we get, current at time 0 is 0 because we haven't closed. I'm closing the switch at time 0, if you're wondering. And so because of that, because the current's before the switch is closed is 0, it must be 0 right after the switch is closed because current can't infinite, if the current was jumping from 0 to something finite in an infinitesimal amount of time, that would mean that the voltage developed across the inductor was infinite, which is not allowed because this is just 9 volts or whatever, So as you guys are well aware, the inductor resists a change in current. And here's a graph of the solution. So I think you guys probably already know this, but just so I'm just reiterating the basics for this, making sure you guys have heard this. The time constant, which is L over R here, is kind of like the time scale of the circuit. And after one time constant, you're that much charged the inductor up. And then after 5 time constants, you're 99.3% of the way to the steady state current, which is E naught over R. Now, eventually, you get very, very close to this, and so the current's no longer changing. You basically establish the magnetic field in the inductor as big as it's going to get, And if you were to that's it. That's what happens. After a long, long time, an inductor looks like a short circuit, right? So we need to talk then about energy and magnetic fields. So the energy in a magnetic field, we can calculate the work done per unit time in a circuit against the back EMF as it relates to the self-inductance, right? So dw dt is minus EL, which is L di dt. Trying to think here. So then we take that and, basically multiply both sides by dt, integrate both sides, and we get W is, 1/2 Li squared. Now this assumes that I have 0, 0, so the energy required to get to the current up to the level I after some time is that much. That's how much energy is stored in the inductor, right? And we understand that energy is stored in the magnetic field, basically. All right? Now, so here's a calculation that's Griffiths is like, all right, well, that's great, but how can we understand this in terms of, current density and so forth? Maybe there's a more interesting formula. And so what he does is he trades out the magnetic field for the vector potential, and then we do Stokes' theorem is equal to Li, right? But then that implies that we can, our formula, it's gone now, but 1/2 L, oh man, dudes. Oh, this is Li, right? It was 1/2 Li squared, right? So this is Li, that's I, this is collectively Li squared. There's nothing too deep going on here, okay? But at this point, he's like, okay, well, let's bring this I over to here and make it an I vector integrated over dl. So if you look at that, you're like, oh, so the analog of this formula for a current density, instead of integrating along the loop, we integrate over the volume, the current density. See the analogy here? So this would be the formula for the energy stored in a magnetic field that's being established by a current density J with vector potential A over some volume, V apparently. And then I wrote do better, but then I had to cross that out because anytime I find myself saying do better, I have to cross it out. Because I just feel like those are words that no one should ever say to another person. Sorry, I'm still scarred from like 2020. But anyway, so this is A dot J, but J is the curl of B by Ampere's law. Notice the mu naught over here. So 1 over, 1 over mu naught times the curl is equal to J. I did that, right? And then, we have the product rule, right? And solving for this guy, right? We have this dot that minus that. But you notice it's b dot b. Why is that? Well, that's actually kind of dumb, right? Because of course, the curl of the vector potential is, by definition, the magnetic field. So this is b dot b, which of course is b squared. So we have, then going back to the previous formula, the energy stored in the inductor is given by, or it doesn't have to be an inductor, it could be any circuit with the current density J, right? 1 over 2 mu naught integral of b squared d tau minus that piece, right? But then if we apply the divergence theorem, we have this. But the thing is, if we go far enough out, right, if we're talking about a finite distribution of current, then this has to eventually go to 0. And we can neglect that, and we're just left with this first piece. Now, of course, if you don't take the integral over all space, right, where the magnetic field is 0 eventually, unless it's not because we're working with one of our toy examples which actually has infinite energy. You know, like I'm pretty sure that if we look at the infinite line current and you calculate the magnetic field, the energy of the magnetic field through all space, I would wager it's infinite if I had to guess. I haven't checked that though, but anyway. This gives us the formula for magnetic energy. We just 1 over 2 mu naught times the integral of b squared over the volume. So that means that the energy density, like energy density per volume, is just b squared over 2 mu naught, right? That would be the magnetic energy density. And we can contrast that to our earlier formula for electric energy, which there we integrated the potential times the charge density over the volume. And that worked out to 1/2 epsilon naught E squared d tau. So this is the electric field energy density, and this is the magnetic field energy density. You can see it from this, like, E squared epsilon naught over 2 or B squared over 2 mu naught. Those are respectively the energy density in the electric or the magnetic field. All right. So at this point, I will do my job. All right, so this part I wanted to write out because it kind of matters more. I think we had to have that discussion about induction in here, because otherwise the discussion of magnetic energy doesn't quite track, right? So that was the reason for talking about induction. It's not so much that I'm going to try to find some like next level crazy circuit for you guys to work out in here. That's not what we're after, right? The homework should show you more what I'm focusing on, right? I hopefully have not done anything too nefarious in the homework. Any questions before I go on? All right, so let me find my,
Oh, I have a question.
yeah.
What is Maxwell's correction?
what is Maxwell's correction term is what we're about to answer. So yes. So let's work that out. So in order to understand why there needs to be a correction, we have to understand what are Maxwell's equations at our current juncture, right? So let us remind ourselves what they are. All right, so we have number one, the divergence of the electric field is charge density divided by epsilon naught. Number two, we have the divergence of the magnetic field is 0. Number three, we have that the curl of the electric field is minus partial B partial T. And number four, the curl of B is equal to mu naught J. All right, so what are we up against here? You guys remember this is Gauss law, right? This one is no magnetic monopoles, right? This one is our most recent addition. This is what? Faraday's law. And this here is Ampere's law. All right? So now, of course, when Maxwell came to these problems, came to these equations, they were not written in this way. And if you were to ask me, well, how were they written? I actually couldn't tell you. I probably should get, I think it's like available as a Dover book. I think there's a Dover book that actually is Maxwell's it's, Maxwell's the author, and I think it has the equations and stuff in there. So you can look it up. But I mean, they're originally 20 equations, and I think they were still kind of like a confusion about the constitutive relations versus the basic fields, and all that was in play, and it was more of like a quaternionic notation or something. The vector notation hadn't come into play. So what Maxwell actually did was not just this. It wasn't so crisp and clean as like what we're looking at. Because we have the modern vector notation, we'll be able to understand what Maxwell did in 5 minutes. It's much more probably hard to see if you're looking at it in the notation that Maxwell had. But the basic thing that we're going to look at is we know something, right? We know that the divergence of the curl of a vector field, this is non-negotiable. This is 0. So this is a fact of vector calculus, right? So we have no choice. We have no choice but to live according to that law, right? And so the question then is, are Maxwell's equations consistent with that identity? And the answer is partly. So if we look at the divergence of let's say the curl of E, well, that's the divergence of the time derivative of the magnetic field, right, by Faraday's law. And then because we can commute partial derivatives, right, we can commute partial derivatives, this is minus the time rate of change of the divergence of the magnetic field. But there are no magnetic monopoles, right? So this is 0, and so we have 0, and so yay. No trouble there, right? But what happens when we look at the curl of the magnetic field? Right? What happens there? If we look at the divergence of the curl of B, what do we get? Well, the curl of B by Ampere's law is mu naught times J, right? And well, mu naught's a constant, thankfully. I mean, there's some debate about that, but it's not a... Anyway, there has been discussion about whether or not the fundamental constants of nature are themselves functions of time. But not in the standard theory anyway. So certainly in this class, mu naught's a constant, 4 pi times 10 to the minus 7, right? The permeability of the vacuum. Is this 0? Well, if J is steady, then we had that the divergence of J was equal to 0, and so we get equals to 0, check, right? So the equations are consistent for magnetostatics, sure. But what if the current's not steady? What if the current density is not steady? Then what? Well, if the current density is not steady, we've got a problem, right? So if the divergence is not equal to 0, then we've got a problem. Can we fix it? Right? You get that? Maxwell's correction term, yes, yes. So let's look at an example where, I'll tell you what, let me do the correction term first, and then I'll do the example second, all right? Now, like I think if you read Griffiths, he does the example, does the mathematics, and then comes back to the example as an explanation, but I'm going to break and just do the mathematics to start with, all right? So what Maxwell realized is that Ampere's law needed a correction term. So Maxwell modified Ampere's law to include a so-called displacement current. Mu naught epsilon naught E. Not E, but partial E, partial T rather. Wait a minute. I think that's right. Oh goodness. Sadness. Yeah, that. Let me be more specific. So he said that Ampere's law was wrong. In fact, this is the real law. The curl of magnetic field is mu naught J. That's still got to be there. But guess what? There's also mu naught epsilon naught partial E partial T. This is the grand, glorious new Faraday's law with Maxwell's correction term. And it's going to turn out that this is actually the real deal. All right? Now we'll talk more about why that's called a displacement current after we get done with a little bit of mathematics here. But to start with, let's see how that fixes the problem. All right? So we go back through then. Let's look at the divergence of the curl of B, right? So that's the divergence of mu naught J plus mu naught epsilon naught partial E partial T, right? With our newfangled law. But then we can pull the mu naught out, and then we have like the divergence of J plus, epsilon naught times the divergence of partial E partial T, right? So I factored the mu naught out. Now we can do the same thing we did in the previous derivation, which is to flip the time derivative and the space derivatives, right? Flippy flop. So this is going to be mu naught divergence of j plus partial t of the epsilon naught, partial t epsilon naught divergence of E. All right. Now that, what are we up against? This, what's this? Yeah. Yeah, Gauss's law says that that's exactly the charge density, right? Because the epsilon naught, they'd be canceling. And yeah, we got mu naught times the divergence of the current density plus the time rate of change of the charge density, like that. Oh man, it didn't work out to 0. Well, this is no good, right? I guess Maxwell was wrong. What do you guys say to that? Well, I covered something the other day in class, and therefore it has been forever committed to your memory, right? Like that's the way this class works. If I say something once, it's indelibly inscribed on your brain. That's just the rules of this class. So, look, this could also be written as, if this was true, right? If this is true, then I get 0 up here, right?
Conservation of charge.
Yeah, that is conservation of charge. So because charge is conserved, that's 0. And therefore, Maxwell's equations, so modified, are consistent. Now, just because they're consistent, it doesn't make them true, right? Like consistency isn't enough. There's all kinds of wackadoodle theories which are consistent, which are still wrong, you know? But this also, you know, satisfies experimental tests and so forth. And so the most basic example that you can kind of see how this is going is the charging capacitor problem. All right, like if we think about, you know, a voltage source, a switch, right? We've got this, I'll draw it cartoonishly big. We've got these plates, right? Let me try to make it here we go. Here's the one plate, right? And here's the other plate. All right. You know, and I'll put some resistor in here, just whatever. What happens as we close the switch at time a little bit positive? You guys know what happens, right? We close the switch, and then the capacitor begins to charge, right? So, close switch. And, you know, current flows, right? For t greater than 0. And so, the problem that you could perceive before that is if you know, you looked at, like here, you know, that particular Amperian loop around there, right? So if we look at that, we have the integral of b dot dl, right? Mu naught j. My bad, mu naught integral of j dot dA, right? Which would just be like mu naught I. So this would suggest that, 2 pi s times b is equal to mu naught I. So apparently b is mu naught I over 2 pi s, right? Which is not equal to 0 when the current's flowing. If we look at that loop, that surface as I pictured it, right? But what if instead of that surface, you were to look at this surface, right? Like, I don't know, I'm failing to capture it. Maybe I have to draw it like, let me draw it like this so you can see it better. So here's the loop I'm talking about. And then I'm saying to bubble it like this. Whee! And then my capacitor plate is here, right? If you can envision that. So the point is, the point is that J is equal to 0 on the bubble. Because the current only flows here, right? The other capacitor plate's down here, all right? So there's no current flowing through this red bubble. So if Ampere's law, without any correction, was true, we get a contradiction. Because if we were to apply Ampere's law thoughtlessly, so naively, this implies B is equal to 0. The same place we just found it was non-zero. Well, that's obviously incompatible, right? That is, this example here, this naive example is an artifact of that mathematical inconsistency. All right? Now let's see how Maxwell's correction term fixes the physics here. See, because Maxwell's correction term says that we don't just do this, we're supposed to do, the integral of b dot dl is equal to, mu naught times over the boundary of the surface is equal to the integral over the surface of J plus epsilon naught partial E partial T dot dA. All right? And so let's talk about these two different surfaces. Let's talk about this one as S1, and let's talk about the red one as S2. All right? Now, if Ampere's law with Maxwell's correction is logically correct, it should give us the same result for any possible bounding surface of the loop. Which seems like a tall order to fill, but that's just what it does. So, let's think about this. For the case of S1, what's the story there? Notice that the boundary of S1 is equal to the boundary of S2, okay? So the integral over the boundary of S1, b dot dl, is mu naught, the integral over S1 of simply J dot dA. E is equal to 0. Where's the electric field here? It's between the capacitor plates, right? So the electric field is 0 for S1. All right? Who was that? Oh, it's easier here, right? Whee! Here's my E field lines, all right?
Isn't S1 above the plate?
S1 is, in this picture, right here. Did I do otherwise?
What do you have up there?
Yeah, it's above the plate. This is the plate.
Oh, I see what you mean.
Yeah. So this is just, 2 pi s times b is mu naught I. Yay. The magnetic field apparently is, mu naught I over 2 pi s. Of course, I'm ignoring, I'm assuming, let us understand, I'm assuming for the sake of just making this formula that we're looking at a wee bitty loop. And so effectively it's a very long straight wire. So the symmetry is sufficient to simply say that this integral goes like that. Otherwise we have no right to use Ampere's law, and let us not talk of that at the moment. All right? So I'm assuming that this is a tiny loop for the sake of using Ampere's law over here in a legitimate fashion. All right, fine. So that's case number 1. Now case number 2, we have integral over the boundary of S2, right, of B dot dl. Of course, these are equal. That's the same set of points. But now we're up against mu naught epsilon naught the integral over S2 of, partial E partial T dot dA. So here, what I'm going to now do, it's a little bit kind of sketchy, but if you guys don't mind, for the sake of being able to actually do the calculation, let's just make this like that through here so that I can just calculate the, let me make the electric field perpendicular to that. Like, let's just flatten the bubble. We can do that. Why? Like, when is it okay to, when is it true, like the integral, when can I do this? Let's say S1 and let's say S2 and S3. Like here's...
When there's no charge enclosed?
Yes, when there's no charge between them, right? So if we have the divergence of the electric field is equal to 0 between them, then the deformation theorem of calculus 3 says that the flux integrals are equal because they differ by an integral over the volume that's between the surfaces, and that volume integral goes to 0 because of the divergence theorem. Okay, so we can reasonably flatten this to make the calculation easier because there's no charge between the plates, right? Whoa. There's no charge between there's no charge between the two surfaces that I'm deforming, right? Let me be careful here. There's no charge here. That's where I'm doing the deformation. I'm not deforming it up here. There's definitely charge here. That's kind of the point. All right. So you guys help me out. What was the formula for the electric field between the plates? Yeah, I printed out Griffiths to try to get me out of trouble here. Let me. Yeah, sigma over epsilon. But I mean, there's a. Oh yeah. Here we go. You are correct, Shane. So let me take a walk down memory lane here for a second. E is sigma over epsilon naught, true enough, and that's equal to Q over epsilon naught A here, which then means that this is actually equal to mu naught epsilon naught integral of what? Partial E partial t is what? dq dt, right? Also known as I, right? So we've just got, I dA over epsilon naught A here, I think. So the epsilon naught's canceling, and we've just got mu naught, and I should say, yeah. I'm an idiot. Mu naught I over A, the integral over S2, right, of dA, which is also A, right? So I get mu naught I A over A. I just get mu naught I, which of course is the same as mu naught I. So up to some simplifying assumptions so that we can actually do the capacitor integral and such. You see that this correction term repairs the seeming contradiction that we got by just using naive. I mean, we never said that Ampere's law worked in the case that the current was not steady, and a charging capacitor is exactly a non-steady current. So this is exactly what we'd expect to happen. So in view of all this definition, right, J sub D is equal to epsilon naught, excuse me, partial E, partial T. This is the displacement current, as it's called. And what's the moral of the story here about this new improved Maxwell's, Ampere's law? What does it have for us? What is the content of this new equation? What is it saying? Faraday's law, what did it say? Faraday's law, in the most interesting case, setting aside quibbling over motional EMF, if we accept Griffith's version of Faraday's law, right? Oh man, stupid. I thought we'd escape the glare in here, but no, the glare is over there. I'm gonna have to move to the middle board. Sorry, guys. You guys can't see the glare, but it is powerful in the camera. So Faraday's law told us that if we have a changing magnetic field, that can induce an electric field, right? Changing magnetic field gives us an electric field. When is the displacement current non-zero? Changing electric field, right? So this is the content of Maxwell's correction. What this says is that a changing electric field creates a magnetic field. And okay, fine. It doesn't really have causation, right? I'm telling the story as if it's the cause, but you could turn the table, right? You could say, anytime I have a curl of a magnetic field in the absence of a current density, there must be a changing electric field. I could start with the B having a certain property and say that there has to be the E. You can go both ways. Which came first, the chicken or the egg? I don't know, but the point is that they're related in this way, right? Well, I guess the egg came first in that case, but right? Usually. You guys think Adam was full grown when he's created? How about the trees of the garden?
Yeah.
So why do you think it took time for the universe to be created?
It's not 6 days.
Well, 6 days, but I mean, like, think about this. Like, if you believe that the trees in the garden were created in their full mature form, why would we assume that there's a process for the rest of the universe to be created? Well, I mean, it was created in the 6 days, is, I think, what's true. But, like, we get all hung up on, like, how did everything get in place and how did the light get from here to there and everything. But if you really stop and think about the garden itself, there's much there. Anyway, what do I know? But that's new, because Faraday's law had a changing magnetic field creating an electric field. But now we see that changes in the electric or the magnetic field create the existence of the opposite field, right? Which is starting to show us what's really going on here is that the electric and magnetic field are part of a unified phenomena, right? They're part of a coherent whole, the electromagnetic field. That takes its full form in chapter 12, which we'll get to at the very end of the course, since when you asked me to. But anyway, I think that's enough for today. So I'll stop there. I don't really intend to cover much more of chapter 7. Like, I'm pretty much starting in chapter 8 next time. There's some stuff about boundary conditions and things, but I don't think we need them yet. So I'm inclined to wait